Colombia, 2009. A coal mine called Cerrejón. A team of paleontologists is digging through layers of ancient rock, compressed remains of a rainforest that existed 60 million years ago. Then one of them stops. He's holding a vertebra, a single bone, and it's thicker than his wrist. They assume it's a crocodile, because what else could produce a bone that size? But the shape is wrong. The curves don't match. They run the measurements again and again. The bone isn't from a crocodile. It's from a snake over 42 feet long, weighing more than 1.5 tons, a snake so large that it didn't just rewrite the record books. It made scientists question everything they thought they knew about life on this planet. Before we go any further, I want you to think about something. We share this planet with the largest snake alive today, the green anaconda, 28 feet long, 500 pounds. A predator so large that most people will never see one in the wild and feel grateful for it. Now double that length. Multiply that weight by 4, that's Titanoboa. And here's what makes this story genuinely unsettling. Titanoboa didn't exist in some impossibly distant prehistoric era alongside dinosaurs and flying reptiles. It existed after all of that, after the extinction, after the reset, in a world that was already rebuilding, already moving forward, which raises questions that science has spent decades trying to answer. What kind of planet produces something that large? What does an animal like that actually eat? How does it move, hunt, survive? And why, after millions of years of dominance, did it simply disappear? And maybe the most uncomfortable question of all, what does the existence of Titanoboa tell us about the world we're building right now? Those are the questions this video is going to answer. The Cerrejón Formation in northern Colombia is one of the most remarkable fossil sites on Earth. It isn't a dry desert canyon or an exposed cliff face. It's an active coal mine, one of the largest open-pit coal operations in the world. And buried within it, layer after layer, is a perfectly preserved snapshot of a Paleocene rainforest from roughly 60 million years ago. When paleontologists first began working the site in the 1980s, they were focused on plants. The compression fossils there are extraordinary. Leaves, seeds, root systems from ancient trees that no longer exist anywhere on Earth. But over time, animal bones started appearing. Giant turtle shells, crocodilian remains, fish vertebrae from species long extinct. And then, in 2009, used a vertebra that changed everything. Narration: the research team, led by paleontologist Jonathan Block from the University of Florida and geoscientist Carlos Jaramillo, recovered dozens of vertebrae over multiple excavation seasons. Ribs, partial skulls, associated fauna that painted a detailed picture of the animal's world. Each new bone confirmed what the first measurement had suggested. This snake was approximately 42 feet long at minimum. Some estimates, based on the largest recovered vertebrae, pushed that figure past 50 feet. Its weight fell somewhere between 2,000 and 2,500 pounds. To put that in terms that actually land, the largest anaconda ever reliably documented in modern times measured 28 feet and weighed around 500 pounds. Titanoboa was nearly twice as long and up to 5 times heavier. The research was published in the journal Nature in February 2009. The scientific community's response was, by academic standards, something close to stunned silence. Because a snake that large doesn't just break records. It asks a question that the bones alone can't answer. How was something like this even physically possible? The answer had nothing to do with the snake itself. It had everything to do with the planet it was living on, and that planet looked nothing like the one we know. 58 million years ago, the Paleocene epoch. The dinosaurs have been gone for roughly 6 million years at this point. The asteroid impact that ended the Cretaceous period wiped out approximately 75% of all species on Earth. The planet is still recovering, ecosystems rebuilding from scratch, food chains slowly reassembling themselves, and the tropics are doing something extraordinary. Global temperatures during the Paleocene were dramatically higher than today. In the region that would become northern Colombia, scientists estimate average year-round temperatures of at least 90 degrees Fahrenheit, with almost no seasonal variation, no cool nights, no dry season relief, just constant, relentless, saturating heat every single day for millions of years. In that environment, the rainforest didn't just grow, It exploded. Trees reached heights we don't see today. Waterways spread into vast swampy labyrinths of tangled roots, slow-moving channels, and warm dark water stained brown by vegetation. And for cold-blooded animals, reptiles, fish, turtles, this world was paradise. Here's the biology that makes Titanoboa possible. Snakes are ectotherms. They don't generate their own body heat. Their metabolism runs entirely on borrowed warmth from the environment around them. The warmer the world, the faster their metabolism. Faster metabolism means faster growth, more efficient digestion, and the ability to sustain a dramatically larger body. Modern anacondas and pythons are already pushing against the upper limits of what our current climate allows. Today's tropics, the Amazon, the Congo Basin, Southeast Asia are actually too cool to produce a Titanoboa. Our world isn't warm enough. The Paleocene was Anna's. When scientists recovered the Titanoboa fossils, they weren't just looking at a giant predator. They were looking at a biological thermometer, a record of climate conditions preserved in bone. The size of the vertebrae allowed researchers to calculate not just the animal's dimensions, but the minimum ambient temperature required to sustain a body that large. The math pointed to a world roughly 5 to 7 degrees Fahrenheit warmer than the modern tropics. Consistently, year-round, the Cerrejón site confirmed this from every direction. Giant turtle shells, some the size of dining tables, early crocodile relatives with heavy crushing jaws, dense plant compression, fossils from trees with no living relatives. This wasn't just where Titanoboa lived, this was the world that made Titanoboa necessary. So we know what built this animal. Now comes the question everyone actually wants answered. What did 42 feet of muscle and bone actually do? How do you hunt when you weigh more than a car? Everything popular culture has ever shown you about giant snakes is wrong. The image of a massive serpent chasing prey across the jungle floor, striking from trees, moving at speed through undergrowth. None of that applies to Titanoboa. 42 feet of muscle is extraordinary in water. On land, it's a different story. That much body weight pressing against the ground fights gravity with every movement. Breathing becomes harder, digestion slows. Forward movement requires enormous effort. In the Paleocene swamps of Colombia, Titanoboa solved this problem the same way a modern crocodile does. It went into the water and it stayed there. The buoyancy of water supported its mass. The warm temperature kept its metabolism running at full capacity. And the murky, tannin-stained swamp channels provided something invaluable for an ambush predator. Invisibility. Titanoboa didn't chase, it didn't sprint. It positioned itself in shallow water between root systems and fallen logs, and it waited, sometimes for hours. Paleontologists believe possibly for days between successful hunts. When something came close enough, a giant turtle crossing a shallow channel, an early crocodilian moving along the bank, a large fish navigating a narrow waterway. The strike was sudden, not dramatic, just decisive. Biomechanical models estimate Titanoboa could generate over 400 psi of constriction pressure. Modern boa constrictors kill by restricting blood flow to the brain and heart. At Titanoboa's size and force, the mechanism barely matters. What it wrapped around didn't escape. The diet at Cerrejón tells its own story. Giant turtles were everywhere, slow, calorie-dense, and abundant. Perfect prey for a patient ambush predator that didn't need to move fast. Early crocodilians were present, smaller than the modern apex predators their descendants would become. Large fish were common in the river systems, and early mammals, still relatively small in the Paleocene, still figuring out what they were going to become, would have avoided the water's edge whenever possible, for good reason. The swamp wasn't just Titanoboa's hunting ground. It was, in every meaningful sense, its entire world. The water kept it warm when necessary and cool when needed, supported its weight, hid its body, and delivered food directly to its position. Remove the swamp, and the animal cannot function, which turns out to be exactly how the story ends. Titanoboa was perfectly adapted, perfectly positioned, dominant in every direction. So why did something that's successful simply stop existing? The answer is one of the starkest lessons in all of natural history, and it has almost nothing to do with the snake. Titanoboa didn't go out dramatically. No asteroid, no mass extinction event, no single catastrophic moment that ended everything in a flash. What ended Titanoboa was a change in global temperature of a few degrees Fahrenheit. That's it. That's the entire story. Beginning around 56 million years ago, Earth started cooling, gradually at first, fractions of a degree per 100,000 years. But for an ectotherm whose entire biology was calibrated to a very specific thermal environment, gradual is plenty. As temperatures dropped, Titanoboa's metabolism slowed. Digestion took longer, growth rates fell. The enormous caloric demands of maintaining a body that size became harder and harder to meet because hunting efficiency dropped alongside body temperature. The animal was essentially running on a generator whose fuel supply was slowly being cut off. Meanwhile, the world around it was transforming in ways that compounded the problem. Mammals, warm-blooded, metabolically independent from environmental temperature, were diversifying rapidly. They could stay active in cooler conditions. They were competing for the same prey that giant reptiles depended on and winning more often as the climate shifted in their favor. The dense Paleocene swamp forests were drying out. Seasonal variation increased. The slow, warm, humid waterways that Titanoboa required began giving way to faster, cooler, more variable river systems. The giant turtles declined. The massive crocodilians shrank. The food web that had supported the largest snake in history was quietly disassembling itself, not through catastrophe, but through slow, steady change. And Titanoboa, exquisitely adapted to a world that no longer existed, had nowhere to go. The last individuals probably didn't die in any remarkable way. They simply stopped reproducing successfully. Juveniles couldn't grow large enough. Adults couldn't find enough prey. The population contracted year by year, generation by generation, until one day there were none. Somewhere around 58 to 56 million years ago, Titanoboa disappeared from the fossil record entirely. The largest snake that ever lived was undone by a shift in global climate so gradual that no individual animal would have noticed it happening, which is, depending on how you look at it, either a tragedy or simply the most honest possible description of how evolution works. Adaptation is specific. Environments are temporary. The overlap between the two is always shorter than it appears. But here's where the story stops being just about a prehistoric snake and starts being about something much closer to home. When scientists published the Titanoboa research in 2009, the headline was about the snake. Largest snake ever found. Record-breaking size. Paleocene predator rewrites history. But inside the scientific community, the conversation was about something else entirely, because Titanoboa is, among other things, a climate proxy, a biological record of atmospheric conditions from 60 million years ago encoded in bone. And the temperature that bone implies was a deeply uncomfortable number. The Paleocene world that produced Titanoboa was roughly 5 to 7 degrees Fahrenheit warmer than today's tropics. That's not an Ice Age scale difference. That's not geological catastrophe. 5 to 7 degrees is a number climate scientists talk about regularly, as a projection, as a warning, as a threshold. The same temperature shift that allowed a 50-foot snake to exist is within the range of changes currently being modeled for the next century. This doesn't mean Titanoboa is coming back. The evolutionary timescales involved are completely different. Millions of years versus decades. Modern snake species couldn't scale up that fast, even if the conditions were perfect. But what Titanoboa does tell us is something simpler and more fundamental. Climate doesn't just influence which animals survive. It defines the biological ceiling of what's possible. It sets the rules. And when the rules change, even slowly, even gradually, the animals built for the previous version of the rules don't get a vote. Titanoboa was built for a specific world. It was built so precisely for that world that when the world shifted by a few degrees, nothing about the animal's extraordinary design could save it. That's not a cautionary tale. It's just how the system works. It has always worked this way. The question worth sitting with is simply this: what are we building for? There's a Titanoboa vertebra on display at the Smithsonian National Museum of Natural History in Washington, D.C. It sits in a case, lit from above, roughly the size of a human fist, thick, dense, unmistakably large. Most people walk past it without stopping, because a vertebra without context is just a bone. It doesn't communicate scale. It doesn't tell you that the animal it came from was longer than a school bus and heavier than a pickup truck. It doesn't tell you about the swamp or the heat or the 60 million years of compression that brought it to the surface of a Colombian coal mine. The bone needs the story. What the team at Cerrejón pulled from the earth wasn't just a record-breaking animal. It was a complete picture, preserved in extraordinary detail, of a world that operated under completely different rules than our own. A world where the temperature determined the size of the apex predator, where the swamp was the center of the food chain, where a cold-blooded animal could grow large enough to be the most dangerous thing in its ecosystem for millions of years. Titanoboa existed for somewhere between 2 and 4 million years before it disappeared. In geological terms, that's a respectable run. Most species don't last that long. It was discovered, measured, named, and understood by a team of scientists working in an active coal mine in northern Colombia. People who came looking for plant fossils and found something that forced them to recalculate what they thought they knew about the history of life. That's how paleontology works. You're never looking for the thing you find. 60 million years ago, a snake longer than 42 feet glided silently through warm, dark water in what is now northern Colombia. It wasn't aware of being extraordinary. It wasn't aware of anything beyond the immediate information its senses were collecting. Temperature, vibration, the movement of water near its body. It was just an animal doing what animals do in the world it was given. The world changed. The animal didn't survive, and 60 million years later, a scientist in a coal mine picked up a bone the size of his wrist, turned it over in his hands, and began to understand what had been living there. That moment, a human mind connecting across 60 million years to a creature that never knew it would be remembered, is one of the quieter miracles of science. We dig. We measure. We ask questions that the Earth answers slowly, reluctantly, one bone at a time. And sometimes what comes out of the ground is something so far beyond what we expected that the only honest response is to run the numbers again and again until the measurement stops feeling impossible and starts feeling real.